If we summarize what machine learning does in the simplest way, it's mostly two things: classification and prediction. Now, we're going to look at the most basic way of making predictions. We have this data set. Let's look at the far right column. That's the house price. The other columns, number of rooms, number of bathrooms, house area, land lot size, and so on. You can guess, right? Yes, these are factors that influence house prices. So, we'll set house price as the dependent variable, and all the others as independent variables. I'll skip explaining those terms. I trust you already know them. Which variable do you think affects house price the most?
Like, comment, subscribe, and turn on notifications.
Let's assume it's house area. We'll explore the relationship between house area and price. We'll put house area on the x-axis and price on the y-axis, then plot the data points. The table here shows just 7 data points, but in my original dataset there are many more. What you see here is about 60 randomly selected points. Roughly, we can see that as the area increases, the price goes up. If I had to draw a line by eye, it would look like this. This green line is purely my eyeballed guess. But a computer can't eyeball a line like we do. Instead, it calculates it very quickly. Let's have the computer draw it. This red line is quite different from my guess. How did the computer calculate this red line? What exactly did I tell it to compute? First, let's look at the equation for the red line. If we call price y and area x, we can write y equals ax plus b. But remember, the y values on this line aren't the actual prices, they're predicted prices, so we'll write y hat like this. In high school, we thought of x as an unknown variable, but in machine learning, x here is no longer unknown, it's our house area data. Same for y, it's our actual price data. Now, instead of writing y hat equals ax plus b, we'll write y hat equals w transpose x. Why w? It's a vector. Don't panic, it's just high school vectors. Here, w is the column vector w sub 0, w sub 1, and x is the column vector 1 and x sub 1. By convention in ML, unless stated otherwise, vectors are column vectors, and t means transpose. It turns a column vector into a row vector or vice versa. When we take the dot product of w and x, we multiply each component and add them up. In this case, w sub 0 plays the role of b and w sub 1 is a. It's the same equation, just written in vector form. Now, let's think about when we have two independent variables. Price is still the dependent variable, but now the independent variables are house area and total lot area. Since we have two independent variables, we'll call them x1 for house area and x2 for land lot area. We can plot price y against these two variables in 3D. When we plot about 60 points, we can see a trend. As house area increases, price goes up. As lot area increases, price also goes up. With one independent variable, we used a line to describe the trend. Now, with two variables, we use a plane to describe it. Why? If we fix x1 at some value, the relationship between x2 and y is still a line. As x1 changes, those lines stack together to form a plane. Let's visualize it. First, I'll zoom in to make it clearer. Now, we'll add the prediction plane for x1 and x2 predicting y. From above, house area versus price goes to positive slope. Lot area versus price also goes to positive slope. The equation of this plane is y hat equals w0 plus w1 x1 plus w2 x2. Looking more closely, the planes equation is just the dot product of two three-component vectors, w and x. W transpose means we lay the w vector down, multiply component-wise with x, and sum. What if we have three independent variables? Then including y, we'd need 4 dimensions to plot, which is impossible to visualize directly. Yes, we could use color to represent y, but not as an actual axis. So with 3 or more features, we can't show the relationship geometrically like before, but mathematically, it's still easy to write. No matter how many features we have, we can still express the prediction as y hat equals w transpose x. If we expand the dot product, it's just w0 plus w1 x1 plus w2 x2 plus plus wn xn. Even when we can't visualize the space, say in 4 or more dimensions, this equation still describes a geometric object called a hyperplane. It has all the mathematical properties of a plane, just in higher dimensions. So, how exactly did the computer find that red line or plane? This red line is our prediction, represented by y sub I hat. The yellow points are the actual values, y sub I. When the computer draws the red line, you can think of it as finding the line that minimizes the difference between predicted and actual values. The difference for a single point is y sub I hat minus y sub I. If we just sum these differences, positive and negative errors would cancel out. So we square each difference to make them all positive. Then we sum all these squared errors across all points. The result is the sum of squared errors. The computer picks the line that makes the SSE as small as possible. The same applies when we have two independent variables and a prediction plane. We find the plane that minimizes sum from I equals 1 to n, open parentheses, y sub I hat minus y sub I, close parentheses, squared. Even with 3 or more features, though we can't visualize it, mathematically it's the same. We're finding the hyperplane that minimizes the sum of squared differences between predictions and actual values. Now, let's compare two related formulas, SSE and MSE. MSE, mean squared error, is simply SSE divided by n, the number of data points. We can rewrite MSE in terms of w, and when we do, we see it's a quadratic function of w. Graphing LW versus W, we get a convex, bowl-shaped curve. How do we find the minimum? Exactly. We take the derivative, set it to 0, and solve for W. That W becomes our model parameters, and the equation y hat equals W transpose X becomes our model for predicting house prices.